Hi, I'm Marcus, and this presentation is about linear programming and bet allocation strategy. Let me clarify first that the presentation is not about promoting or encouraging gambling in any way. The focal point is a description of a concrete mathematical methodology for the optimal allocation of an initial amount of units, or money, of course, to a predefined number of individual bets. Now, how should we distribute this initial amount of money? Setting the target. We need to allocate this amount of money in such a way that if we win a minimum number of those bets, of those individual bets, we at least get our money back. We break even. Of course, I'm not referring to parlays, because parlays are combinations of bets that win or lose as a unit. Okay, in order to win the parlay, you need to win in every single bet in the parlay. If you lose just one, then the parlay is lost. The bets I'm talking about are single, individual, independent bets. This means that the outcome in one bet does not affect the outcome of the other bets, in any of the other bets. Of course, this is very easy to do. This calculation is very easy to do when all the bets have the same odds. Let me show you. I have prepared a spreadsheet. In this column we have the odds, which we assume that they are equal for all the bets. This is the total amount of units. This is the number of the events, and in this column the minimum number of the bets that we need to win is calculated, so that we don't lose money. Of course, in many cases, even if we win a minimum number of bets, then not only we get our money back, but we also get some profit. As you see, let's put 5 in here. As you see, when the odds are small, then we need to win a big number of those bets, even all of them. As the odds increase, then the number of the bets we need to win is becoming smaller. In this case, for when the odds have the value of 1.7, then we need to win at least 3 of the bets. Let's put here 8. As you can see, when the odds, all the odds have, all the bets have, the odds of all the bets, is equal to 2, then we need to win at least 4 of them to break even. Now let's put this spreadsheet away and get back to the real world, because in the real world this doesn't happen. In this case, what do we do? The answer is to apply linear goal programming. And let me demonstrate using an example. Let's assume that we have an initial amount of units that are equal to 100. That is equal to 100. And we need to place these 100 units to 5 individual bets. Every bet has its own odds. The odds are expressed in decimal format. I will not be using any other format, fractional or American style. And of course the goal is to put our wagers in such a way that we at least break even if we win a minimum number of bets. Let's describe the problem mathematically. Of course, the sum of all the wagers must be equal to 100. And let's assume that in the first iteration that we need to win at least 2 of those 5 bets in order to get our money back, no matter which 2. In this case, for all combinations of 5 bets by 2, we need to get our money back. These are the equations. First and second bet, if we win the first and second bet, we get our money back. The first and third bet, we must get our money back, and so on. Of course, this formulation is unrealistic and probably infeasible. Definitely infeasible. Okay, so let's convert this set of equations to a linear programming problem. We will do that by introducing 2 extra variables, an L variable and a p variable. L represents loss and p represents profit. Every combination of those bets has its own loss and profit variable. Now for the first combination, there are three possibilities. Of course, we break even. In this case, the return, which is the sum of those two terms in the equation, is equal to the amount of money we place. Okay, and L1 and P1 are equal to 0, both of them. The second possibility is that the combination wins, but we don't get back our initial amount, but less money. So in this case, in order for the equation to balance, we need to add the loss. L and P variables are greater or equal to 0, of course. Okay, we need to add the loss. Now, but if the combination wins and we get back more than our initial amount of units, then in order for the equation to balance, we need to subtract the profit. Of course, the optimization problem is a minimization problem in this case. We want these equations to hold true by minimizing the sum of all individual losses. Okay, if we solve this optimization problem, then the answer is that the value of the L function, I'm using LP-solve by the way. Okay, this is an optimization library. The minimum value for the L function is 163.28. This means that there is absolutely no way we can at least get our money back if we win 2 bets in any combination. It's impossible. So we move on to the next iteration and we do the same thing now for every combinations of the 5 bets by 3. As you see now, these terms are 3 in every equation. Okay, 2 bets per equation, 3 bets per equation, and we optimize the exact same problem as before. In this case, we find out that the minimum of the L function is equal to 0. This means that all L variables are equal to 0. So it's possible to break even with 3 winning bets, no matter which combination wins. And of course, we have the solution for the x variables too. Okay. But now that we are positive that no matter which of those 3 combinations win, do we need to apply this solution? Do we need to accept this solution as the final solution? Well, no. We reformulate the problem. We know now that the L variables are equal to 0, so we get rid of them. And we only need about the P variables, the profit variables. And we change the problem in such a way that we maximize the total sum of the P variables, the profit. And we get back another answer. Let's see those answers. Of course, the algorithm stops in this case. Okay. Now, in this column, the green values are the amount of the wagers for the minimization of losses problem. In this column, for the blue values for the maximization of the sum of profits, and this is the average. Now we can have an average. In fact, we can have any linear combination of the solution of the 2 columns is also a solution to the problem, because the equations are the same. Of course, we got rid the L variables in this case, but the L variables are equal to 0. So every solution of this problem and the next one, we can combine linearly and produce another solution. In this case, the average. I'm taking the average as the combination. Okay. If we apply this solution, of course, in some cases we profit, in other cases we just break even. If we apply this solution, I will be discussing the zero number here later in the video. Okay, if we apply this solution, then a different distribution of and values for profits is calculated. In many cases, we break even when in the minimization problem we have a profit. In the maximization we just break even. In this case, in combination number 2, we profit in both cases, and so on. But by applying the average solution, we can still profit in every case. This doesn't happen all the time, but if we use the average solution, at least we can be on the profit side in more times than we can be by just applying the solution of the minimization problem or the maximization problem. Okay, now let's review the procedure. First, we identify a number of individual bets and their odds. We formulate and solve the linear programming problems and minimize the loss function for all combinations of bets by 1, 2, up to m. M is less than or equal to n by 1 to m items until the value of the loss function is equal to 0. We can accept the solution of the loss minimization problem as final, or eliminate the loss variables and maximize for the profit function. Of course, we can also accept any of the previous two solutions as final, or calculate a new one, which is the linear combination of the two original solutions. Okay. Now let's discuss the advantages and disadvantages of the method. The advantages. It's a conservative strategy, not to lose. We don't want to maximize profits. We just want to get our money back. Of course, it's better than flat betting. Anything is better than martingale. Martingale is a recipe for disaster, if you ask me. And we can have more efficient bankroll management. Disadvantages. It requires software to implement, of course. BetCrash is a software program I will be discussing in the next part of the presentation. It's conservative. This is both an advantage and a disadvantage depending on the point of view of the player. It's not value betting, does not guarantee long-term profits. Okay, the individual bets need to have value in order to achieve that. But in my opinion, the greatest disadvantage is that this methodology may lead to a false sense of security. The player might think that he or she has a safety net and can afford to lose bets and even make bad decisions. Okay, in the previous case we only need to win 3 of those 5 bets. So a player might think that okay, let's place a bet in an impossible. Let's choose an impossible bet with impossible odds, with impossible probability. Okay, so he might think that there's nothing to lose if he loses the bet. But in this case, he has to win 3 out of 4 in order to at least break even, and not 3 out of 5. I mentioned BetCrasher. BetCrasher is a software application that does exactly that. This is the application. I wrote the application. Of course, there wasn't any application there that used the procedure I described earlier. So, in order to construct a collection of bets, of course we add a bet. We give it a code. It must be unique for all the bets in the collection. A date, an hour, let's say 7 o'clock, 7:30 in the afternoon. Bet description: A team versus B team, home win. Home win. The booker name, and odds. And let's add the bet to the collection. Bet number 2, again the same. C team versus D team, over 2.5 goals. Booker name, odds 1.9, and let's add this to the collection, and so on until we finish. Okay, now let's load the example I discussed in the first part of the presentation. This is exactly the example. Okay, now let's produce the minimization. Let's generate the minimization problem for the two bets. These equations can be. Let's copy the code and let's go to LP solve. We can paste the equations here. Okay, and solve the problem. This is the optimal solution. We want to minimize the sum of the losses, and of course, as you see, the L variables are not equal to 0. Some are, some are not. Let's go on and generate the linear programming problem for for 3 items per combination. Okay, let's copy the code. Let's go back to LP solve. Paste the problem and solve it. Now, as you can see, the optimal solution is 0. All the L variables are equal to 0, and this is our solution. And the P variables, the profit variables. The X variables, the bets, and the profit variables. Of course, no. We need something. This is not practical. We can generate the linear programming problem and solve it this way, but it's not practical. It must be done automatically. We can do this by pressing this button. Okay, and we have all the solutions available right away. These are the bets, the individual bets. Minimization functions, the minimization of the loss function, maximization of profit function, and the average, and so on. If we apply the first solution, we win 6 and we have profit in 6 out of 10 situations. If we apply the second solution, we kind of profit in 7 out of 10 combinations. But if we apply the average solution, then we can have profit in all combinations, no matter which of those combinations wins. And of course, the minimum required to winning bet number is 3. Let's apply the average solution. Update. These are the amounts. This is how we split our initial 100 units. This solution is very easy to verify. Let me show you how we do it. This is the return column. This is calculated by the odds times the amount of the bet, and this is the return. Now, if we choose, if we mark as successful the 3 bets with the smallest return value, and this combination of bets adds up to 100 or more, then the solution, then this will apply to all the combinations. For instance, this is the bet with the smallest return. The second, the smallest is this one, and that one is the last. Of course, we need to change row for the calculation to update. So we see that for those three bets, we get back 105 units. We are on the profit side. This means, of course, that we will be on the profit side, not only just get our money back, for any other combination. These values are the three smallest values. We can round the amounts of the bets if we want, but we need to do it manually. Okay, and now let's go back and discuss this zero. This zero, excuse me, this zero means that it's possible to decrease the number of the events, the number of the bets by one, but not win 3 out of 4, but 2 out of 4. Let me show you. If we don't include bet 3 in the formulation, as you can see, we only need to win 2 out of those 4 bets in order not to lose money. This is the number 2. Okay, we can apply this solution if we want, or stick with the original 5 bets and win, and require 3 of them to win in any combination. Okay, this is the we can set minimum and maximum constraint for the bet, for every single bet if we want. I don't have something else to show to you. Let's generate 10 bets and see what happens. Number of bets is equal to 10. As an example, odds between 1.9 and 2.5. Interesting. 2.5. The software accepts odds only in decimal format. Let's clear the existing collection and generate the problem. Our initial amount of units is 100 again. Let's solve the problem. This is the solution. We need to win 5 of those bets in order, in any combination, okay, in order not to lose money. You see now that if we apply the minimization solution, the minimization of loss solution, then we can profit in 50% of those cases, of those combinations. If we apply the maximization profit solution, still 50%. But if we apply the average solution, then we can have a profit in 72% of those combinations. Okay, and that's it. This is a big number, of course. You see, as we increase the items per combination, the number of combinations is very big. Let's choose 5 and generate a problem. It's a big problem. Copy code. Let's put this code back to lpsolve, and lpsolve, see how big the objective function is. Let's solve the problem. As you can see, for 5 bets, the loss function is 0. This is the solution, and this is how we distribute our initial amount, and these are the profits for every combination. We can either break even or have a profit. Now, I don't have anything else to discuss. you can the bed crasher is free to download and use. Okay, I will the link will be I will the link is in the description of the video. Should you find any bugs, please notify me. This is the end of the presentation. Have a nice day, and the social message of the video is: don't gamble. I wrote this program for fun. Okay.